Okay, now we're going to be dealing with, for lecture 2, the dependence of rate on concentration. And here's some terms you should know. Now the top one is going to be really important. The rate law is the rate times, or the rate is equal to K, and then, let me write them all out. The rate is given in molars per second. Should know that. We already talked about that. And then we have this rate constant. It's a proportionality constant. Then each A, B, and C are reactants. And then we have their coefficients up on top. And each reaction has its own rate law of that form. So when we look at the first problem, we have that reaction. What can be said about the rate law? Well, what we can say is that the rate for this reaction is equal to K times the concentration of bromine raised to A. We don't know the exponent yet. F2 is B. So that's all we can say. You might say, well, we have a 1 here. Isn't that a 1? And that's a 3. Shouldn't that be a 3? No. We cannot look at the reaction and know what these exponents are, or what K is. Sometimes it happens that, if we did this, once we find the rate law, which is one of the things we're going to do, if this turns out to be a 1 and a 3, that would be just by chance that it is. But usually the numbers are either 0, 1, or 2. So, and usually the coefficients are no more than 3. So a lot of times, just by chance, they'll happen to be the same, but we can't count on that. So that's the rate law, and it's very important to know that directly from the reaction, we cannot tell you what the rate law is. We have to calculate it. The rate law for the above reaction is this. So I'm saying, well, what if it happened to be where the exponent for bromine was 1 and the exponent for fluorine was 2? What is the overall reaction with respect to each species, or the order of reaction with respect to each species? And what is the overall order? So the order of reaction with respect to bromine is 1. Whatever this, now this one, since we have the rate law, we can read that directly off. The order of reaction with respect to fluorine is 2. So if they don't show a number here, then we just assume it's a 1. And that's it. This is the easiest problem in the whole course. Getting the order of reactions, students still get it wrong. If I ask for the order of reaction with respect to a species, look at its exponent in the rate law. That's what it is. Done. The overall order equals 1 plus 2. Just add them up. Don't multiply them, don't divide them, don't do anything else, add them up. So it's 3. And that's all there is to it. If you have a rate law, and we'll just make it general. So you had this. Let's say it's 3, and this is C is 1/2. Then what's the order for? And you can have fractions. We don't use them, and you can have negative numbers. That does come up. So what's the order of reaction with respect to A? -1. For B, 3. For C, 1/2. What is it for the total? 1.5. It's going to be 3 minus 1 plus 1/2. So that's 2 plus 1/2. What did I say? So that'd be 2. Yeah, glad I did it out. So the 4 halves. So actually it'd be 5 halves. Those fractions can get a little tricky. That's the overall. So the order of each species, look at its exponent. Overall, add them up. Done. That's all that there is to it. Now, what's a little trickier is finding K. This one, let me just rewrite it. Now, remember, the rate is molars per second. And you can make it moles per liter per second if you need to. I like to leave it as molars as long as I can. Actually, in this case, just to be complete, let's do it that way. Moles, M per S is moles per liter per second. Yeah, this is better to expand it out so you can see everything. Now, this is a concentration, so that's moles per liter. Yeah, that's a better way to go. And this is moles per liter squared. So I didn't put any numbers in here, but the units are on their own, and it doesn't matter what the numbers are. They're going to cancel against each other, not with the numbers. So we can just put in the units. That's a very common thing to do, and find the units of K. So what you do, moles per liter per second, K, and this is going to be moles cubed over liters cubed. Then K is going to be moles per liter per second. Remember, we're going to flip this, so it's going to be so this is going to be liters over moles. Liters cubed over moles cubed. That changes to 2, so does that. It's liters squared, moles squared per second. Very odd units, but that happens when you're dealing with these rate laws. You can see that the units for K, since these always have to be moles per liter per second, that K, the units for K, are going to depend on how many, what these exponents are. The larger these exponents, the more weird looking the units are going to be for K. But we got to just get used to determining what those are. Now let's see, let me just double check, make sure that I got everything here. Yeah, looks good. Okay, let's go to 2. Here, determine the order of reaction for all species. So here's just another one to do. Determine the order of reaction for each species, then the overall reaction, and then determine the units for K. So for oxygen, that is 1. For nitrogen, -1. For fluorine, 3. Overall, 1 minus 1, 3, so the overall is 3. And once you get good at it, you can see you can just do it from up here. I mean, first you can find these, but the overall is 1 minus 1, 3, so it's 3. And usually it's going to be a integer, it can be negative, but there can be fractions in there. I might put some, the only thing that can make it really tricky are the fractions like you saw there. I kind of misguessed there when I tried to do it in my head. So for fractions, and anything like this, even for this on an exam, if I were doing it, I'd spell it all out and take my time with it. But they're generally not too bad, and especially if it's all positives, it's hard to make a mistake. All positive integers, I should say. Now, what are the values for K? Well, one thing that could help you is that since this is moles per liter, and this is the inverse, this would be liters per mole, so they're going to cancel. So you don't have to deal with this term. But let's say we don't know that. And I should have enough room here. So we have rate. Let me do it down here. Just do it all the way out. Okay. Now the rate is moles per liter per second. And it is better to break it up now that I've been working with these again. It's been about, about 6 months, 7 months since I did these, so got to be careful. Now that I've done it out, it's better to break it up into moles per liter. Just you're going to have to cancel, so it'll be easier to do that if you have them separated out. Now this term, if we rewrite it, that'd be the inverse. So we just the reciprocal. Just now it's this term is the same as this now. Just got rid of that negative by flipping it. So these cancel. And this is still moles per liter per second. Make sure I'm on the screen. And I'll be careful. I'm been doing a lot of videos this summer, so I'm pretty good about keeping everything in frame. But if it falls below the frame, if I haven't deleted the video, it means that eventually I'll show it. So it shouldn't be too much of a problem. Now, we want to isolate K. So we do it by putting this, getting rid of those terms on the right side. So those will cancel. K is then equal to, just flip, all I've done is just just change the equation around. A is equal to B, so B is equal to A. So just flip the equation. Don't have to do anything weird with the units to do that. Just trade places. Now, liters cancel. This is now to 2. Moles cancel now to 2. So this is liters squared moles squared per second. What was the last time? Oh, that was just by chance we end up with the same units. I don't want to get the idea that that the units for K are always the same. We'll see some different ones, but It's just we don't have a lot of exponents we can work with. Theoretically, the number can be anything. But in reality, it's usually somewhere between -3 and 3. And really, most of the time, it's 2, 1, or 0. But we can have negatives. Now, we don't want to do anything further with that. We want to go into finding the complete rate law with data. So we've done out what we can with just the rate law as is. Now we have some data to work with. And this gets a little trickier. So if we said that we can't look at the reaction and determine the rate law. Can't do it. We have to use some data, empirical data from from experiment. So we have the rate law here. We know is going to be of this form. Like that. Now, what we're trying to do is determine A, B, and C. And that's the phone if it's making its way in there. I forgot to shut it off. So A, B, and C are what we're after, and we're going to use this data to determine them, what those exponents are. Once we have those, then we're going to be able to determine K. So it's a fairly lengthy process. Now I'm going to do it out longhand, then I'm going to show you the shorthand way of doing it. When I do that, you're going to hate me because the shorthand way is very simple. But I want to show you, I want you to understand why you can use any shortcut. Anytime we use a shortcut, you should know why it works. Now what we're going to do is we have 3 exponents that we're after, so we're going to need 4 experiments to find them. If we have 4 exponents, we need 5 experiments. If we have 20 exponents, we'll need 21 experiments. We'll always need one more. And one of our experiments is going to be the base. You don't have to circle it or anything like I'm doing, but I'm just showing you that. Notice that these have the same concentrations. And what we're going to do, experiment 2, look at what happens. We double the concentration of fluorine. We leave bromine and oxygen alone. By doubling fluorine, then we can see what happens to the initial rate. By doubling fluorine, the initial rate doubled. That actually tells us that the exponent for fluorine should be 1. That's just what it means, but I'm going to show you how we get that. So what you do is you take the rate for experiment 2. And that's going to be equal to K. And we plug in the data from experiment 2. Now he said, well, why didn't we start with 3 or 4? Start with whatever you want. I'm going to start with experiment 2 because that's going to allow us to find fluorine. We can only find 1 at a time. So you can see we're going to use 2 and 1 to find fluorine, the exponent for fluorine, 3 and 1 to find bromine, 4 and 1 to find oxygen exponent. So I'll put in the data. We have 0.4. I changed the square brackets to parentheses because now we have an actual term in there. We don't know what A is. The concentration for bromine in experiment 2. And if you have a lot of questions right now, that's fine. You should if you haven't seen this before, but it will make sense as we go along. Now, rate 1, the first of experiment 1, K doesn't change. That's what's going to help us out here. The concentration for fluorine is 0.2. We still don't know what its exponent is. But notice what's the same in experiment 2. All of these concentrations are the same. They're all 0.2. Now, here's where we get a little tricky. Let's take we want to divide this equation by this equation. So if you do that, then get rid of those. And this is like any math equation. You can take the left side of one equation divided by the left side of another equation and right side by right side. So we're not doing anything crazy here. This is just some basic math that we're allowed to do. So the rate 2 divided by rate 1 is equal to their rate laws over each other. Now we know what rate 2 is. I left it off first, but we can go back up here. The rate for experiment 2 is 0.0300 molars per second. Rate for 1 is 0.015. Now, before I put in the rest of it, you see that K's cancel. And then notice that even though we don't know what these exponents are, these are the same number raised to B, so those cancel. Same number raised to C. And that's why we leave bromine and oxygen alone, their concentrations alone. We only change one concentration at a time, because then everything else cancels. We're left with this. We're going to get rid of the units here. They don't get carried through. And then this is to the A power, and that's just 2 to the A. And we see on this side, 0.03 divided by 0.15 is 2. And these units cancel. We're left with 2 raised to the A. So what does A have to be equal to? 1. So we found the exponent, and that's how we do it for each of them. But notice, anytime you double the concentration of any species and the rate doubles, that exponent is 1. We've shown it mathematically. By doubling the concentration, the rate doubles, then the exponent is 1. That just means that by doubling the concentration of something, if the rate goes up, then it's first order as far as its rate law, or it's first order in its it's first order as far as its participation in the rate law. So there is a list in your book of, let's look at the next one here. Let's see if, before we do it. Bromine, if we double bromine, so this is our base, everything's 0.2. We go to experiment 3, fluorine and oxygen stay the same, so they don't affect reaction rate. We double bromine, and its rate doesn't change. That means its exponent is 0, and let's prove that now, just to show you. So we'll do this a little quicker. It's going to be the rate 3 over rate 1. So rate 3 is 0.015. And I'm going to leave off the units because we know that they cancel. Now we know that they cancel. And the rate is... Now, we already know what the exponent is for fluorine. I'm going to leave off the molars because we know they cancel. So top and bottom, A is 1, and we know that for 1 and experiment 3, this is 0.2 for the fluorine. For bromine, rate 3 has been doubled. We still don't know what its exponent is. So because we know what A is, that saves us a lot of hassle. We don't have to put A here. We know that's just, we've already found it. So anytime you find one of these exponents, use it. This is 0.2, and I'm just saving some room on the paper too by doing this. But you can see these cancel, K's cancel. This is 1. Get the right significant figures. 1 is equal to 2 to the B power. Simplifying. And the only way 2 can be equal to 1 by raising it to the exponent, B is equal to 0. So anytime you see that the rate doesn't change for a species, when you double it, and we double it so that the only reason that we're doubling it is so that we always have powers of 2. We could triple everything, then we'd be powers of 3. Those are trickier to see. It's easier to look at this data, and if you see that the concentration doubles and the rate doubles, that's easier than tripling this and seeing that the rate triples. But we could use any, and you don't even have to use these values. You just have to make sure that you change only one at a time. If you wanted to change this to 0.715, it'd be a nightmare to do, but you could do it out this way. You could do it out mathematically and get the right answer. But we do it this way. By doubling it, we can then just look at the rates and figure out the exponents. Now let's look at, so we know what B is now, it's 0. We have, when we double oxygen, the rate goes up 4 times. That means that C is going to be equal to 2. But let's do it out. The rate is for 4. We're rate 1. I have a bad feeling we might have to finish this up on another video. Sorry if we have to do that. I want to keep it under 20 minutes. Now the concentration for fluorine is 0.2 in both cases. I'll put it in here, but since the exponent is 0 for the bromine, we don't even have to put it in there. Anything to the 0 power is 1, so we don't even have to put it in there, but I'm putting it in there just to be complete. For C, we double that. Oops. And we can see that it's 4 is 2 to the C, so C is equal to 2. and we'll find K in the next video.